NCAR. She's a project scientist there with the Research Applications Lab, where she works on a variety of cloud physics research projects, spanning topics from aerosol cloud interaction to cloud microphysics modeling and parameterization improvements. She also manages the Idaho Power Cloud Seeding Modeling Study, which is the focus of her presentation today.
Good morning. Everybody hear me okay? Thank you for accommodating my travel troubles that I had and moving me to today. So I'm going to be talking about some of the work that we've been doing with Idaho Power. I'd like to acknowledge my co-authors on the slide, Lynn Shu and Roy Rasmussen from NCAR, as well as our fellow colleagues from Idaho Power. They're representing them today for us. We've been working on some modeling work for the winter orographic cloud seeding that they do, so we're going to switch from some of the summary convective talks of this morning now to winter. So the motivation for us doing this work was threefold. First of all, we wanted to see if we could develop a system that would automatically declare and execute cloud seeding simulations in a real-time forecast model. So Idaho Power has been working with the University of Arizona for quite a while to run a real-time forecast model to help guide their operational seeding, but it has never explicitly forecast the seeding signatures itself. And so that's what we're going to do using the new silver iodide seeding parameterization that was developed into the WRF model, the Weather Research and Forecast Model, by Lynn Shu and other co-authors, built off of Akihiro Hashimoto's model, as well as in collaboration with the Wyoming Weather Modification Program and the Idaho Power Program. I'll talk just a little bit more about that parameterization in the next few slides. But some of the other benefits for having this in real time then is that we can estimate the potential precipitation enhancements from a given seeding period prior to that event using this forecast. And then that can then provide guidance to cloud seeding operators on those potential seeding opportunities. It can help guide them in times to look for and turning on seeding, the method of seeding, whether it should be ground-based, airborne, or a combination of the two, which location. In the case of Idaho Power, I'll show you there's 3 different target areas that they're working on, and so we can look at which is the best location for a given time and so forth. So to go over briefly a little bit about the seeding parameterization, there's 2 papers that are coming out in the Journal of Applied Meteorology and Climatology. Lynn is the first author of those papers. So that describes this parameterization in much more detail. But this parameterization does have several key microphysical features. First of all, it can simulate the fraction of silver iodide that nucleate ice crystals by 4 of the 4 nucleation modes: deposition, condensation freezing, contact freezing, and immersion freezing. These are parameterized in the model following DeMott and Myers parameterizations. It also simulates the scavenging of silver iodide by cloud droplets and ice crystals following Caro et al. It can also activate cloud droplets on the silver iodide, so they serve as CCN in some situations due to their soluble fraction from the burning of the seeding solution. And the cloud seeding parameterization has been coupled in the WRF model in the Thompson microphysics scheme. So that's the key microphysics scheme we need to use with this seeding parameterization. This diagram is taken from Shu et al. 2013, just kind of showing all the different pathways, microphysical pathways that take place in the model for these new species that were added to track the silver iodide, both in dry form, which you can see here in the center, and then in each of the different hydrometeor species like raindrops, ice, snow, grapple, and cloud droplets. So we include things like scavenging, melting, riming, the different nucleation modes of immersion freezing, contact freezing, and so forth. Just to kind of give you a quicker glimpse at how this model works, I'm going to show you an animation here where we're simulating an aircraft track flying from the northeast to the southwest here, and then it turns around and flies back towards the northeast. As this animation goes through, these light blue colors that you see are the concentration contour of the silver iodide. The yellow contours are then ice crystals. And then you'll see some green here, which is the actual snow. Now I want to point out we've changed the contour level on this to be pretty high because there was some background snowfall occurring on this day. So just because you don't see very much green doesn't mean there wasn't that much snow falling. But we upped the threshold so you can kind of see more directly some of the snow that was converted from the ice crystals that nucleated. This whole white field here is the area of cloud water. So this simulation or this animation will start again so you can better see that as that aircraft flies along and puts out the silver iodide, once it gets into the areas of the cloud water, it quickly will convert into ice crystals. About to start again, I think. Here we go. So there's silver iodide. In this area of cloud water, you'll start to see the yellow start to form. That's the ice crystals being nucleated by the silver iodide. Same thing happens up here in the northern portion. And some of that does get converted into snow as well. And one other thing that I would like to point out is that downwind, you'll see some of the silver iodide show up again. Let's see if it's going to happen here at the end. Yeah, here we go. And this is just a process of, as it's evaporating back, you're getting those silver iodide particles. So those silver iodide particles are tracked all the way through the species, both in the wet form, in cloud droplets or other type of hydrometeor species, as well as back in the dry form.
Sir, what's the topography?
What's this topography?
Yeah, what are we looking at?
This is a case from Wyoming. I'm trying to remember, and I'm not as well versed on where it is. Is it the medicine bows?
It kind of looks like that might be Elk Mountain.
Yeah, we did this specific run in the, I think in the LES version that he was running for one of the case studies from Wyoming.
Thank you.
Just to put it, and this is just an artificial flight because you guys didn't do any flights. We just wanted to kind of show more explicitly how this converts more directly. So we can run this point source seeding parameterization like I just showed you from aircraft. You can put a line of AGI into the model at any given time and place. We can also do it from the ground for ground-based seeding generators as well. And so what we're doing now is we're putting this into a real-time forecast model. I mentioned earlier that Idaho has been running a real-time forecast model with the University of Arizona. So this model that we're running with them now is 1.8 kilometer horizontal resolution over the full model domain, and I'll show you that domain in a moment. It's using NAM forecast for initialization, and the key thing there is the Thompson microphysics scheme because that's what we have this seeding parameterization in. So the model is run every 12 hours, 0Z and 12Z. We do have a control run all the time, running every 12 hours. And from that control run, where there's no seeding implemented, we determine if seeding conditions are optimal with an automatic real-time seeding decision algorithm. And so if the seeding conditions are optimal, then we run a second forecast run every 12 hours at those given times, either 0 or 12Z, with the seeding implemented. And so I'll talk a little bit more now about this seeding decision algorithm because that's what we're really working on improving right now to make sure that it's identifying appropriate times for seeding, identifying the proper methods and so forth. And we're doing this with two sets of criteria, microphysical criteria and dispersion criteria, and I'll go over those in the next few slides. But first, let me just show you this model domain. So this colored map here is the full model domain. It's a single grid that I mentioned, 1.8 kilometer resolution. The three areas that we're running the seeding decision algorithm on are the Payette River Basin here. The actual basin is the black outline and white outline, but this white box is the full domain that we're running the algorithm over to determine if optimal seeding conditions exist. You can see in this basin they have ground-based generators as the little white circles, and they do aircraft seeding in this basin. They have a number of potential flight tracks which are identified by these blue lines. And so the algorithm will determine in this region which of the best flight tracks should be flown if the airborne seeding is optimal, and if ground-based generators should be turned on or off as well. Then the other major domain is in the upper Snake River Basin, this eastern Idaho area. We've divided it into two domains for the algorithm just because it's such a large, expansive area. So we've got the northeastern Idaho here identified by this white box, and southeastern Idaho by this other white box. In eastern Idaho, they do ground-based seeding only. You can see the scattering of ground-based generators. But we do have a couple flight tracks which are probably kind of hard to see on here. One's just north-south oriented, another north-south oriented, and then one here at an angle. We put those in the model just to do some testing to see the feasibility of airborne seeding in those regions. So if we do airborne seeding in those regions, it's all just fictitious in the model for right now. So I mentioned those sets of criteria that this real-time decision-making algorithm uses. The first is just based on microphysical criteria, things that you would expect to be in place for silver iodide seeding to be efficient. So each of these criteria has a specific range of values that must be met, as well as a specified areal fraction over each of those white boxes that those values must be met for. This latter criteria is fairly ambiguous at this point. This is our first year that we've developed this, and so the areal fractions that we've assigned for some of these values might be too low, too high, and this is going to be part of our refinement in the upcoming months as we've completed now this seeding season and we look back on all of our cases. And I'll go over some of those examples in a bit. But as you would expect, key microphysical criteria that need to be met. We need to have liquid water, so we look at liquid water path and supercooled liquid water content in certain altitude ranges, whether it's near the surface for ground-based seeding or in the altitude of flight for airborne seeding, as well as supersaturation with respect to ice, and temperature is another key criterion as well. In this algorithm so far, we have a weighted algorithm, but these two latter criteria, supersaturation with respect to ice and that temperature range, those two have to be met. Those are mandatory fields for a seeding case to meet the microphysical criteria. In addition to meeting microphysical criteria, we also set some dispersion criteria, because if you have especially ground-based seeding, you need to make sure that it's not too stable, that the particles will actually get up into the cloud, as well as that the wind's going to blow them into the right place. So these are pretty much criteria that look at the wind speed and wind direction. For ground seeding, we also look at some stability parameters. For airborne seeding, it's just pretty much the wind speed and wind direction, with the wind direction helping us determine which flight track is going to be the optimal one to choose for that particular case. So we started running this system on November 1st, 2012. We've been running it all the way through the winter season, and we're just now starting to wrap up. I think we stopped running the seeding model at the beginning of April. We've done some statistics here that go through February 26th. As I said, there's 2 forecasts each day. So we've had 118 days so far, which equals 236 control forecasts. Of those 236 control forecasts, 139 of them have called at least one seeding case in one of the 3 regions, either ground or airborne. Now, during this period, 11 real cases were actually seeded in the operational seeding program. Don't be too alarmed by this disparity yet, because a real seeding case typically lasts 12, maybe 24 hours or more, whereas this seeding forecast is run every 12 hours out 48 hours. I did forget to mention these are 48-hour forecasts that we're looking at. So if a seeding case is being very well forecast, it can show up in multiple runs of that forecast. And I'll give you an example to show you when that happens. So this is a little bit inflated due to this duplication of running a new seeding forecast every 12 hours out for 48 hours. However, we are still calling more cases than we probably should. I'll show you some scatter plots of which cases we're going to try to refine the algorithm in order to not be calling in the future. But so here we can see for each of those 3 regions, we've got the Payette, ground versus airborne, the northeastern Idaho, ground versus airborne, and southeastern Idaho, ground versus airborne. The number of seeding forecasts for each of those, as well as the number of actual seeding cases, where a seeding case is defined as when the seeding gets turned on or off for ground-based seeding, or the flight time, how many flights have we done for airborne, as well as the average time for each of those. You'll notice the average time for the flights is always 2 hours. That is set in the algorithm, that the flight cannot be any longer than 2 hours, and it will always be 2 hours. So we also have, in addition to that limit on flight time, we have a mandatory 2-hour downtime after a flight. So when I show you some of the time series plots, you'll see if there's multiple flights being called, it's 2 hours on, 2 hours off at a minimum, 2 hours on, and so forth. Right now, you can see, especially for Payette, we've got a lot of seeding flights being called. Our algorithm also does not have any limit to the number of seeding flights that are called in a given 24-hour period. That's probably not realistic. We've talked with Idaho Power about in this future iteration of the algorithm, refining that to make it a little bit more sophisticated so that we're not telling the pilots to go up and fly 4 or 5 times a day and trying to choose maybe the best 1 or 2 cases. Because if we have a really long optimal seating period, our algorithm doesn't know we should only do 1 or 2 flights, and it just picks the first one, up 2 hours, down 2 hours, up 2 hours, down 2 hours. Most of our ground seating, you can see average time ranges anywhere from 10 to 12 hours, which is pretty similar to some of the ground seating real cases, although some of the real cases often go up to 24 hours if it's a really long, prolonged event. But again, these are just average times. So I wanted to show you a couple examples. This first example I'm going to show you was from December 12th, and it's a good example to walk you through how the algorithm and the forecast works out well in advance of an actual case. So on this particular case, while it was not actually seeded, it's not a real seeding case, talking to Idaho Power forecasters, after the fact they said, you know, looking back, this 8 to 13Z time frame on December 12th would have been a really optimal seeding period. The conditions looked pretty good after all. So we're going to look through this case for a Payette ground seeding example. This first time series plot that I'm showing you is for the 48-hour forecast that starts at December 10th at 12Z. So this was the first forecast that showed this optimal time window of 8 to 13Z, which I've outlined here in the magenta box. And this time series is showing you hour 3 through 48 in that 48-hour simulation that started at December 10th to 12Z. Each panel of these time series shows you each of the key microphysical criteria that must be met, and we're looking actually at the areal fractions. So the areal fractions of, say, liquid water path that's greater than 0.01 milliliters, for example. And the dashed lines on here indicates that areal fraction threshold that must be met. And I mentioned earlier that that's fairly arbitrary right now, so we're doing a lot of analysis on these type of plots to see, are we meeting those areal fractions very easily, maybe too easily, and so forth, so that maybe we need to up them if maybe that would help us remove some of the more moderate cases. As well as we're going to be investigating some of our actual thresholds themselves, like our temperature range probably is, we've decided, is probably a little bit too broad and includes a little bit too warm of temperatures. This is some of the analysis we'll do as we refine the algorithm. But anyway, on this case, you can see in this optimal time window, at 48-hour forecast, this model is doing a pretty good job of forecasting all the microphysical criteria is being met. Now, if a case was being called, it would show up in here as a shaded in gray area. The reason why we haven't called a seeding case in the model for this particular period is the dispersion criteria wasn't met yet. But the model is doing a very good job 48 hours in advance of letting us know that the seeding criteria, microphysically, is looking pretty good. If we move forward 12 hours, that 12-hour window here, or that 8 to 13Z window is moved forward a little bit. And you can see, once again, microphysical criteria are still being met. So this model is doing a very good job at being consistently good at forecasting this event. However, there still wasn't sufficient dispersion criteria for our algorithm, so it still didn't call a case. At this same time, let's take a quick look. Oh, let's move forward. Oh no, this is the airborne one, but you can't see the gray. Derek, this happened in some of our conference calls and meetings. Well, this kind of stinks. So let me try to walk you through what we should be seeing here. This is the exact same time we just looked at, but it's for the airborne seeding criteria. And there should be a very thin, actually there should be 3 very thin gray bars that span 2 hours, down 2 hours, and then 2 hours, that pretty much covered this time period here. If you look at these peaks, yeah, I don't know if dimming the lights is going to help, because I just do not see it on the screen at all. I see it on this screen beautifully, though. Don't know why that happens sometimes. Actually, yeah, I'm going to use this to help guide it. So at just before hour 33, there's one at right here at the end of this, circling this magenta line here, there's another small band, and then just after hour 39. So this was an example actually where there were 3 flights being called. Again, each one kind of aligns with these peaks in this particular criteria, if that helps as well. Because these seeding criteria were being met over this extended period of time, but we have that case being limited by 2-hour flight. So what we've decided is what we'll try to do as we make this algorithm more sophisticated is create a way for the algorithm to look through at the whole seeding period and determine the best 2, maybe 1 or 2 times, rather than just choosing the very first one, you know, as soon as it meets the criteria and calling a flight. Maybe it should hold off and wait for one of the later periods. 3 didn't ask a question, Bruce. Okay. All right, so once again, we're moving 12 hours later, and this is looking at ground again. And unfortunately, you can't see the really thick gray band that starts at about 17 hours in the forecast period. It goes out to about 37 or so here. So it's a very long, wide gray band that covers.
Check if you quit the show mode, probably will show it smaller.
No, that doesn't help. I don't know why it does that. Because I'm not using a Mac. This is actually a PC now too, so it's just the figure. Or the way the projector doesn't like to see that color. Yeah. Anyway, so we've got a very long, extended ground-based seeding case being called by the model in this forecast, which this forecast is now December 11th at 12Z. It fully encompasses that optimal period that the operational forecasters identified. And so again, the models continue to perform very consistently at identifying the microphysical criteria, and now the dispersion criteria have been met, and thus this model forecast had a seeding case called. If we move 12 hours forward again, we would still have a case that's starting from about 5 hours and going out to about 24 hours in the forecast, fully encompassing that optimal time period identified by the forecasters. So now this is 2 seeding forecasts being called just for this one case. So this is another example of where we have this duplication in some of our current statistics. But the model is still continuing to perform well. If we look at it for aircraft, we have actually only got 1 seeding flight now, and it's just here at the end of the period at about just basically encompassing this last magenta line here, this 2-hour period around 12 to 14 hours in the forecast. So they've actually, because the airborne criteria were reduced a little bit, they only called 1 flight in this particular forecast run. And this was at December 12th at 0Z. If we moved forward, I'm not going to show the next one, but if we move forward to 12Z, then the optimal time window, it would be, the forecast would have started right in the middle of it, and we did call another case for that one, but it was much shorter because we were already in the middle of the case period. So looking at some of the results from this case, I mentioned earlier one of the benefits of running this model in real time is we can actually simulate what the precipitation enhancement would be even before the event happens. And so this is looking at a map of the precipitation change difference between control accumulated precipitation and the precipitation in the seeding simulation for the 48-hour period that began on December 12th at 0Z, so the plots that we just showed. So this includes that 1 really long ground seeding case and 1 airborne flight for the Payette, as well as it did have some seeding over here in eastern Idaho. But I'm just going to focus on the Payette since that's the plots we were just looking at. So there was actually an increase in precipitation from the simulation of 1637 acre-feet, which would be a 16% increase over the control precipitation within this Payette area. And I already mentioned, yeah, that included the ground seeding from 6Z to 1Z and 1 2-hour flight. So when we look at all of those 139 seeding forecasts and see how the seeding effect looked for all these different cases, here we're looking at now a plot of the control precipitation across the whole domain for the whole 48-hour seeding forecast versus the total domain percent seeding effect. So now looking at total domain kind of reduces some of the percents on occasion just because we're targeting those smaller regions, but the whole domain, if you have precipitation outside of that, those domains, it can change your precipitation or your percent increases a little bit. But what we're looking at here is we kind of have this exponential relationship where the higher your control precipitation is, the lower your overall percent seeding effect is. This is somewhat intuitive because your control precipitation is your denominator in that percentage, but we'll look on the next slide at the absolute precipitation improvements as well. But I would like to highlight, we've got this region down here where we have low total control precipitation and we still have pretty low percent increases. These are the kinds of cases and forecasts that we really want to try to avoid as we improve this algorithm because it's doing a very good job at identifying just the most minimal seeding opportunity, but it might not be the best. And obviously we're not going to be able to really seed every single one of those. So if this is really going to be used as guidance to the operational forecasters, it can't always be calling every little case that's going to give you just the slightest bit of increase, right? But you will notice that some of our biggest impacts are still in this lower overall control precipitation type of scenario. And when we look at this on an absolute amount, so again, we still have the total control precipitation here in acre feet. Now we have the seeding effect calculated in acre feet. So it has nothing to do with the actual control now. You can still see, there's obviously a lot more scatter, but you can still see that for the highest overall control precipitation or natural precipitation, you're not getting your highest, largest absolute enhancements in precipitation. For the more moderate range, you're getting a little bit more of the moderate range of the enhancements, but really you're getting your biggest enhancements in an absolute sense when you have the lower overall control precipitation. This makes sense intuitively because the reason why we're cloud seeding is because we're saying that these clouds are not being efficient on their own, and so they need a little bit of help, some more ice nuclei, for example, in the case of wintertime orographic seeding, to help them produce more efficient precipitation. And so you would expect the cases maybe that are going to produce widespread heavier precipitation are already a little bit more efficient naturally and may not need as much help from the silver iodide. But once again, I do want to just highlight this group down here, these guys, we want to get rid of them. We don't want them to be called from our algorithm in the future because they're kind of the false alarm cases right now that the operational forecasters are like, yeah, the model, it doesn't know what it's talking about, it's calling everything. And it did, it called everything that just had the slightest ability to produce an effect. Okay, so I do want to go through one more case study here just to look at this. I just grabbed one of our more big effect cases to look at it more closely. This one was on February 12, 2013 at the 0Z forecast. In this particular 48-hour forecast, there was one pay at ground seeding event, 3 airborne flights, 1 ground seeding event for the northeastern Idaho, and 2 in the southeastern Idaho. In this event, again, we're going to look at some statistics for the full domain, for the full Snake River Basin, which is the full river basin in southern Idaho, and then just for our 2 target areas, the Payette and the full eastern Idaho. The top line here is the controlled precipitation, that natural precipitation that the model predicted. This middle one is the absolute precipitation change in acre feet, and the bottom then is the percent change. Anything stand out there and make you jump out of your seat? Okay, so this is the model simulating it. We have to do some verification for the model, definitely. But what's happening here is this was a case where overall very low control precipitation was being forecast, but there was a lot of super cool liquid water and liquid water path in the model that could have been tapped, and when we did put silver iodide in, it was tapped to produce a lot more precipitation. You'll notice overall that the actual absolute numbers in the Payette are fairly low. It's a small domain, whereas eastern Idaho is a much larger domain too, so we do have some differences there just because of the overall size of the domain. But relative to the natural precip in Payette, we did get quite a bit of increase in the simulation. So let's look at this example a little bit closer. This is the forecast liquid water path. I grabbed 18 UTC because this was just a few hours after the ground seeding had been started. I looked at several hours after this too, and it was just pretty much this widespread area of liquid water path, although unfortunately my lowest shade of purple is not showing up, because all of the Payette region is pretty much this very pale shade of lavender. As well as there's a lot more pale lavender throughout here, so my color scale on here is being poorly represented again. But you can see then over here, this is a precipitation change map that we've looked at already for another case. You can see that Payette was very well targeted, and the precipitation change was really focused around the Payette, as well as there was quite a bit of precipitation change here positively in the eastern Idaho area. You can see some down here as well. This day was really unique because the winds were coming more from the northwest, so the plume was flowing from the Payette, plume from the ground seeding and stuff was flowing towards the southeast. And so some of this enhancement down here, due to the liquid water path, was from silver iodide that had dispersed from the Payette region toward the southeast. But I'll point out here, let's look at some observations. So there's a B on here. That's where Boise is roughly, and they have a radiometer at Boise. So we're looking now at a time series of the Boise radiometer data, the integrated liquid water path from the ground. At 18Z, you'll see this really nice spike up to around 0.18 millimeters. And sadly, that light sheet of lavender isn't showing up, but the second one luckily is. And you can see that that is showing up in right over Boise, and lo and behold, it's just below 0.2 millimeters. So at this one snapshot in time, we did a really good job. I mean, the model is saying that there's liquid water there, and the radiometer is confirming it. There's also radiometers at Mud Lake and Afton, so we have 3 radiometers in the full domain to do these kinds of analyses to help verify the model, as well as we have snow gauges and soundings to help do some more verification. So on a seasonal total, and I will first mention seasonally, since we have that overlap in the forecast, we've stitched these together by accumulating the precipitation between hours 3 and 15 in each of our 48-hour seeding forecasts, so we don't have the duplication here. This is the total control precipitation, precip change, and percent change for each of these domains. And so you can see overall so far, the model's doing pretty good seasonally in enhancing the precipitation from control by calling seeding at optimal times for both the Pitt and the eastern Idaho region. All right, so to summarize, we have implemented this WRF-based cloud seeding forecast system. It's been developed and it's been operating in real time this whole winter season for Idaho Power. We've observed already that the seeding opportunity detection using this algorithm is very good. It's identifying pretty much anything that looks like it's possible for seeding. But because of that, it's been identifying actually more seeding opportunities that have been called by the human forecaster. These weak enhancement scenarios in particular are the ones that are being called that we need to try to refine the algorithm so that it's not calling those. So our future work is to evaluate the system at the completion of the full winter season, which is wrapping up right now. So that's going to be our objective over the next few months. We're going to be comparing the model with observations, such as I showed you that one snapshot with the radiometer, but we also have soundings and snow gauges to look at. And we want to improve the algorithm to lower those number of cases being called, but while maintaining the high impact cases. We also want to improve the sophistication of the system for airborne seeding, like I mentioned. And we'd like to conduct a field program in the coming years to help really verify the model, to get some of those more in situ measurements, to not only verify that the model's getting the control criteria, like the liquid water path and so forth, but also to really try to help evaluate the model's ability to simulate the cloud seeding process itself. So I'd like to thank you for your attention. I'd like to acknowledge this work's been funded by Idaho Power, and I hope that you guys find it interesting and maybe applicable to some of the other seeding operations that are going around. And I see a hand waving back there for a question.
I had a quick question for you, but let's see what happens. Is the WRF seeding module ready for summer clouds?
Not at this time. We don't have any projects to work on trying to implement it for summer clouds. But summer clouds that are being simulated by silver iodide, there's potential. The biggest challenge there, I think, will be in the model's ability to forecast summer clouds. Because with winter orographic, you get the nice synoptic forcing, and so the model in general does a pretty good job in forecasting those. Summertime convection is so much more random that as a real-time forecast model for summertime convection, I think it would be challenging. As a way to retrospectively analyze cases from summer, there's probably maybe a little more promise there because we can set things up in a more idealized fashion based on just a sounding from that day or something.
Second, how is the model dealing with ice aggregation? I didn't see in this slide the mention of ice aggregation.
It includes aggregation. Yep, it's included. So the ice crystals aggregate to snow, just like one thing I didn't mention, why we're using Thomson microphysics, and Thomson microphysics includes all of those processes, especially aggregation to snow. The reason why we're using Thomson is because it's been developed primarily from the aviation icing industry, so it's been developed to be able to forecast both wintertime scenarios as well as supercooled liquid water. And a lot of other microphysics packages don't forecast the supercooled liquid water as well, and of course that's key to the cloud seeding process. And so that's why we're using that particular one as well.
Thank you.
Bruce? I'd like your approach, Sarah, to quantifying the effectiveness of ground-based aircraft seeding. But I'm wondering, given your approach, if we can maybe extrapolate from that and look at the duration of airborne opportunities and use that to work backwards to see if and when would ever be worth having more than one aircraft.
That's also, yeah, sure. And this is something, so the algorithm, like I said, for even the other regions that they're not doing airborne seeding, it's more just to kind of test the feasibility of how often are the conditions better there. In the papers that I mentioned, the Shu et al. Papers that present this algorithm, or not the algorithm, but the seeding parameterization, we've done a lot of sensitivity studies, and one of the key things that we found is that airborne is much more efficient in targeting the precipitation enhancement to your region, because you can get the airplane right in, close to the region, in the optimal seeding, temperature and liquid water content, whereas the ground-based plume, you're kind of much more at the whims of the wind, and it disperses much more broadly, and so forth. Downside is there's cost and the limits on time. So you can run the ground-based seeding generators for quite a while. But.
A couple comments. Can you compare the water content versus the amount of control precipitation? I think you're kind of doing it indirectly that the big precipitation events are not containing much liquid water. You can enter into comparison there. Secondly, you're showing downwind effects of cloud seeding in a positive sense. I think that's probably an important point to make, and if you could aggregate how often that's occurring and maybe under what conditions, it would help Joe Golden write his paper about downwind effects of cloud seeding.
Yeah, we've definitely, Lynn has been working on that with the Wyoming projects too, I believe. And that's one benefit of the model, is you can see where the AGI disperses to. If it's not just in your target region, which is, there's no boundaries in the atmosphere that says it has to stay there. And you can see what those effects are. And it generally is fairly positive. The more unstable the wintertime scenario, more convective and unstable it is, the more that we'll see a little bit more noise in the model as far as the positive and negative response. But it's not, we've never seen a widespread negative response.
Thank you very much, sir. Okay, we'll move to a break now, but before we do, excuse me, I ask you to thank our speakers again for some fine work and some very interesting presentations. So thank you. So we have time for a break.